SwayamPrabha. Digital India. Educated India.
So welcome to lecture 9. So in this particular lecture, let us look into some more interesting stuff. Okay. So the topic of this lecture will be thermodynamic properties. Properties in dilute limit. Okay. So far what we have done is that we have used Maxwell-Boltzmann method. We have used Maxwell-Boltzmann method. Okay, to investigate FD, that is Fermi-Dirac, and BE, which is Bose-Einstein statistics, for an isolated system of independent particles. Okay, and what we got from that is, this is the first expression that we got. I write it closely. All right, and the equilibrium distribution particle distribution, which is also written as Mj is equal to Gj divided by Swayam share J minus mu by Kt close means plus 1. Okay, so this is the equilibrium particle distribution, and this was the number of particles, the distribution of particles, or the thermodynamic probability. Okay, now in the dilute limit, okay, we define something called a dilute limit. So what is that dilute limit? Let us look at it carefully. If Gj is much greater than Nj, that means the degeneracy is much greater than the number of particles in that particular energy level, that is few particles as compared to energy states. So it is like a stadium, right, where there are a lot of seats, okay, but only very poor attendance, for example. Right? Very few people have shown up. Okay, so there are very few particles as compared to the energy states that are available, right? So under this condition, both Bose-Einstein and Fermi-Dirac statistics, distributions, okay, should collapse to the same result. Okay, it is rare. Why does it collapse? Because it is rare to have more than one particle in energy state, right? So the Bose-Einstein and Fermi-Dirac distributions should collapse to the same result, it is rare to have more than one particle in any energy state. It is almost impossible. Okay, so for the dilute limit to be valid, Gj must be much greater than Nj. This is the criteria for the dilute limit. Okay, so as you can see that there are lots of seats available in a stadium. So it's unlikely that more particles, two people will start sitting on the same seat. So they will probably occupy one seat apiece because there are a lot of seats available. So that is the reason, while Bose-Einstein statistics does not have any limits on the number of particles per energy state, but Fermi-Dirac statistics actually says that it can be only one particle per energy state. But because there are a lot of states available, okay, the Bose-Einstein statistics and the Fermi-Dirac statistics therefore collapse, okay, and they should give you the same result. But this will only happen when the degeneracy is much greater than the number of particles in that particular energy level, right? So therefore, ln Gnj plus minus 1 is basically the same as ln Gjnj. Okay, and then of course ln 1 plus minus Nj by Gj is almost equal to plus minus Nj by Gj. Okay, this comes from the fact that ln 1 plus x is almost equal to x. Right? So therefore, ln in the dilute limit is basically nothing but summation j nj ln Gj by Nj plus 1. Okay, so therefore, in the dilute limit, Gj raised to the power of Nj by Nj factorial. Okay, so this is the final step that you get. So this has got we can call this the Boltzmanns, coming from Boltzmann. Boltzmanns. Okay. So Maxwell and Boltzmann basically. Okay. So Nj identical but distinguishable particles can be arranged in a single energy level Ej along Gj energy states. Okay. There is no limit on number of particles per state. Okay, so Wj, as we saw, was Gj Nj. Wa, these are the Boltzmanns. Okay, the Boltzmanns. Okay, now if you compare this expression, okay, if you compare now this is what Boltzmann did. If you compare this expression with the one here in the dilute limit, you will see that basically there is a factor Nj which is off. Nj factor, right, is off. Okay, that is because in comparison to bosons and fermions, we do recognize that distinguishable particles, a new microstate is formed when the particles are interchanged among the energy levels. So this is where, Boltzmann got it wrong, because he assumed that the particles were distinguishable, right? So in comparison, so if you say, so this is where the Boltzmanns are different, what Boltzmann did in comparison to to bosons and fermions, comparison to bosons and fermions, okay, we do recognize that for distinguishable particles, a new microstate, okay, is formed when particles are exchanged. Among energy levels, because they are distinguishable. That is where Boltzmann got it slightly wrong, right? And that's why, the results, the bosons became very different. Okay. So now that we have seen that what the dilute limit looks like and how how the fermions and the bosons behave identically in the dilute limit, let us look at a new definition now, which is called the partition function. Okay, so once again, for Gj much greater than Nj in dilute limit, okay, Nj is equal to Gj exponential mu minus Ej divided by Kt. Okay, now Gj is much greater than Nj only when Ej is much greater than mu. Okay, so Gj is much greater than Nj, but this happens only when Ej is much greater than mu. Okay, but recognize that Ej is always positive, right? So the dilute limit clearly applies when mu is less than 0. The chemical potential is less than 0, right? Therefore, mu less than 0 is a characteristic of ideal gas. It's a characteristic of ideal gas. So therefore, Nj exponential minus mu by Kt equal to Gj exponential minus Ej by Kt. Okay. So this is just a simple separation. Now sum over all J, that is sum over all energy levels. What you see is N E minus mu Kt, right? Because we have summed it over all energy levels. This side, of course, is J, Gj exponential minus Ej by Kt. All right. Now, this particular term, okay, this is N E minus mu by Kt is equal to, let me write it again, Gj exponential minus Ej by Kt. This is called Z, where Z or Z is a molecule called the molecular partition function. Okay, this is the molecular partition function. So the molecular partition function is nothing but sum total of these terms over all energy levels. Okay, now if take Nj minus mu by Kt, okay, if you divide it by N exponential minus mu by kt. Okay, that is nothing but basically gj into exponential minus ej by kt divided by z. So what is this particular term? This term that you see over here is basically the jth term of the partition function. It's the jth term of the partition function. It's the jth term, right? So therefore, or in other words, nj exponential nj by n is equal to nj by n, because this cancels out. Nj by n is gj exponential minus ej by kt divided by z. Okay, so nj by n is actually given as this. Okay, now, so this means this is like a population fraction, right? A population fraction. Okay, so it's a population fraction is given by the the jth term of the molecular partition function divided by the partition function itself, right? So if you call it, so this is like the population fraction for jth energy level, okay, is given by the jth term of the molecular partition function divided by the partition function itself. Got it. So similarly, you can also write it as nj by nk. So this is the relative population in energy level j and k, or the ratio of the two is gj by gk exponential minus ej minus ek divided by kt, right? So this is the relative degeneracy and this is the relative energy difference. Okay, so this is like the ratio of the number of particles in energy level j versus energy level k, which is equal to the ratio of the degeneracy at those two levels and the exponential of the differential of energy between those two levels. I mean, each ek energy levels differential. Okay, so z, once again, let us write it unequivocally in a very large fonts, gj exponential ej by kt. Okay, so if you look at it carefully, the jth term, what does it physically imply of the partition function? Represents the relative probability that a single particle, okay, will be in jth energy level. Okay, so this would be that a single particle will be in the jth energy level, okay, is given by the jth term of the partition function. So the jth term in terms of physical interpretation represents the relative probability that a single particle will be in the jth energy level. So that is how you should interpret it. And what about this particular term, this exponential term that you see? So this is E minus E by kt, this particular term that is there in the exponent, okay, is basically like a weighing or a weighting multiplicand that accounts for the influence of temperature on the accessibility okay, of each energy level. Got it? So this is like this, and in the limit, when temperature goes to infinity, okay, this just becomes Gj. So what does this essentially imply? That if you look at this particular expression very clearly, there is a degeneracy term and then there is a multiplicand which sits. This multiplicand is given by the energy. So higher is the energy, lesser is the probability of this particular term, right? In that particular way. Okay, higher the energy. So that means, okay, so this would essentially translate to that this particular term is like a weighing fraction. So not all energy levels has got equal probability, which is kind of understandable. The relative probability of a particle being at a higher energy level is comparatively a little lower, right? Now, when this temperature, however, becomes infinite, okay, this means that this particular term essentially drops out and the partition function essentially becomes the sum total of all the degeneracies, sum total of all the microstates. Now, the role of temperature is essentially, this particular role of temperature is essentially, it regulates that whether the higher energy levels or all the energy levels are accessible to the particle or not. So if it is low, then the higher energy levels are comparatively less and less accessible. Okay, but when it is high, all the energy levels becomes equally accessible, and therefore you don't need this term at all. So this weighing fraction is no longer required when you actually have a situation like this. Now, at thermodynamic equilibrium, thermodynamic equilibrium, Ni by N naught, okay, is equal to exponential minus Ei by E naught divided by Kt, where Ei minus E naught is definitely much greater, is definitely greater than 0. Okay, so therefore Ni is N naught. So the population inversion is, so Ni, basically what does this implies is that Ni is therefore cannot be more than N naught to begin with, right? Okay, the relative. So the population, this also implies that population inversion is non-equilibrium in nature. It's not an equilibrium situation. Okay, non-equilibrium in nature. I think this is quite clear from this particular estimate, whatever we have shown here. Okay, so the criteria for dilute limit for DL is, one is of course your Gj being much greater than Nj, and exponential Ej minus mu, this also we did, by Kt is much greater than 1. That means exponential of Ej by Kt is much greater than equal to 1. Okay, as Ej is greater than equal to 0. So the dilute limit is ensured. Okay, if your exponential minus mu by Kt is much greater than 1. So therefore Z by N, which is nothing but exponential minus mu by Kt, is much greater than 1. Okay. Now, for ideal gas, mu is much less than 0. Okay? So therefore Ni by N naught is equal to exponential minus Ei minus E naught by Kt. So put a couple of brackets here. As T approaches 0, that means the temperature goes towards 0, E goes to N E naught, and E is further equal to Nj into Ej. So the value of E naught is needed to evaluate any properties involving U. So the value of E naught is needed, right? Okay, to evaluate any property as a matter of fact. Any properties involving U, this is itself, not any properties involving U. So we take E naught is equal to 0. Therefore, U is equal to 0 at T equal to 0. Right. Okay. The E equal to 0 when T equal to 0. Right. So, this is the time that we will, in the next class, do a problem on this degeneracy. So you have gone through the steps now. Just to do a brief of recap, this is the relative probability, which is given by the ratio of the degeneracy and this ratio of the weighing fraction. This is the total molecular partition function, and which represents like a relative probability of a single particle will be in the jth energy level. And this acts like this particular term, the exponential term, is like a weighing multiplicand that accounts for the influence of temperature on the accessibility of each energy level. So that is important. And at high temperature, this particular becomes just a sum total of the degeneracy. Okay? And you can see from this expression that Ni by N naught, since this is always greater than 0, this actually proves that this cannot be valid. So therefore, population inversion is a non-equilibrium process in nature. And lastly, if you just do a bit of a recall that what is your partition function. So this is the definition of your partition function. So these are the terms of the partition function. Okay. It can also, the partition function can represent, is like a population fraction representation for the jth energy level. So these are the different quantities that you have. And this is also to note that, at absolute 0, the internal energy is also equal to 0. So we end this particular lecture here, which is lecture 9. And after that, we will do a couple of problems on this partition function before we move any further. So we will see you in the next class.